Okay, so now we're going to revisit the concept of momentum and its relative angular momentum. Okay, it's keeping with our theme of going from translational concept of physics to rotational. So I want to say, before I get too far into angular momentum and the details, I want to make a very important statement right now. Angular momentum and linear momentum, while they're related mathematically, are independent of one another. They are two different aspects. Unlike kinetic energy and rotational energy, which are similar aspects of the same thing. Okay, so that we're going to see that's important down the road. All right, so let's get into it because I really want to focus on conservation of angular momentum. So what is angular momentum? Well, it's the angular counterpart to linear momentum, right? So I've already kind of given it away. So there's angular momentum, and its symbol is capital L. I have no idea why, but we'll live with that. Okay, so the relationship between linear momentum and angular mathematically is that they are cross products, where L is the linear momentum component times some radial lever arm, if you will. Okay, and as such, it can be expressed as the following. Okay, so that can be mv cross r, right? Usually written mvr, which since the cross product, it's really mvr sine of the angle between the two. Usually the angle is 90 degrees, so it just becomes mvr. Okay, now a less obvious way we can write that is in terms of angular quantities. So what I can do is I'm going to cheat a little bit, right? I'm going to take the MVR, okay, and do this. I'm going to do the following. I'm going to do the MVR, which we have, multiply it by R over R. And I say, why on earth would I do that? Well, R over R is 1, so I haven't really changed anything, but let me rearrange this now. Let me write that as MR squared. Whoops. This is kind of a convoluted way of doing it, but it works. So that becomes MR squared, right? I've just combined this term, and this term, times V over R. Okay, which is this term and this term. Well, I hope he recognizes mr squared as the moment of inertia and V over R as omega. So, not surprising is that angular momentum is similar to mass times velocity. Instead of mass, we have moment of inertia. Instead of velocity, we have angular velocity. So that's a fairly common way of looking at it. This is less common, but it is important you recognize it, and we'll see some situations. Okay, as such, we can write the second law of motion in terms of angular momentum. Okay, so the second law of motion in terms of linear momentum, remember, is F is the rate of change of momentum. So we're going to see, rather than F, we're going to call it torque, right? Tau is equal to the rate of change of angular momentum. Okay, so that's nice. And another way we can rewrite that is tau times t, yeah, I know they look very similar, is equal to change in L. So there is a change in angular momentum. Well, that's the rotational equivalent to an impulse. Okay, so the AP is very fond of looking at graphs that have torque and time on it. We'll try to do one or two examples either now or in the homework. Okay, and most importantly, okay, and this is stemming from this, if there is no change of momentum, or I take that back, if there is no torque external acting in a system, then that means there can't be a change in momentum. In other words, angular momentum is a conserved quantity when there are no external, and here we have to be careful, I'll say it now, torques. If there are no external forces, then linear momentum is conserved. But you can have an external force and no external torque and still conserve angular. So we have to be really careful about that. Okay, so mathematically, I've already written here sigma L equals sigma L prime, which usually translates to I omega naught, or I'm not going to forget about the naught, equals I, oops, I mixed up there, equals I omega prime. okay, we will see, I'm sorry, I should put an I prime there, is that you can change the moment of inertia of an object fairly easily, especially if it's flexible. Think of a human being, especially when they're diving. They can change their body position, which changes the moment of inertia. As such, they can change their angular velocity. So we'll do an example like that in a bit. So I'm going to jump right into what I consider a really important problem, right? I've got the 5 stars there, so you know. Okay, so mathematically, we have sigma L equals sigma L prime. All right, so that translates to the following. Sigma L is usually the initial moment times the initial angular velocity, and that's going to equal a new, potentially new moment of inertia, and therefore a new angular momentum. So you might ask, well, why would moment of inertia change? It could change by changing the shape of something. Or if you have a rotating platform and you throw some mass on it, if that mass comes from above and doesn't apply an external torque, then the moment will change, and therefore the object will spin faster or slower, usually slower because the moment will go up. So we'll do some more problems with that idea. But let's turn our attention now to a really important one that we're going to see because it covers a lot of ground. Okay, so basically we're going to have a collision. All right, but in this case, we have a collision of a ball of mass m coming with velocity v hitting the end of a stick, and the stick is free to rotate about a frictionless pivot point. Both the ball and the stick have the same mass. I did that for convenience sake. Instead of writing big M, little m, we can just keep things in terms of little m. And we can ask a few questions, namely, what's conserved and what's not conserved. And based on what's conserved, then we can ask, what's the system going to do afterward, motion-wise? Okay. Oh, also, let's make clear, the ball is going to stick to the stick. All right, that just makes the math easier. It doesn't really change the physics. Okay, so I could ask, is angular momentum, L, conserved for the following systems? All right, let's take the meter stick only. Well, that should be pretty clear in the sense that before the collision, the meter stick's just sitting there, so it has no angular momentum. After the ball hits and sticks, it's going to start rotating, which means it has some angular momentum, I omega. And therefore there's more momentum than we started with. So the answer should be clearly no. I'm going to give a different reason besides what's going on with their angular velocity. So let's look in terms of external torques. If we define a system as the stick, before anything happens, there's nothing acting on it. After the ball hits, okay, the ball is going to exert a force this way due to the collision. Here's our lever arm, R. So in other words, there's an external torque. Okay, so we have an external torque from the ball. Okay, now that's pretty straightforward. Now, let's change our system to include the ball and the stick. Is angular momentum conserved? This is a little less obvious. So you might say, okay, after the collision, they're both rotating, so there's definitely angular momentum. Before, neither were rotating, so there is no angular momentum. But that's not quite how it works there. We got to be real careful about that. So, spoiler, the answer is yes. Why is there yes? Okay, so here's one way of looking at it in terms of motions. The ball is coming in with a momentum mv, and it is hitting the stick not at its center of mass, but at some distance away from its pivot point. So it's hitting it at some r away. So if I include the whole system, then there is angular momentum before there's any collision. Angular momentum is simply mv cross r. And that's really important. You know, I would not expect you to see that right away, but it's important you recognize that now. If the ball were coming in and hitting right there, then there would be no angular momentum counterpart because there's no r to talk about. Okay? Perhaps the easier way to understand why it's conserved is there an external torque to the system? Well, the only torque that's going to come in is the ball hitting right here, as we talked about before, but since we're including the ball as our system, there's no external torque. That's an internal torque. So I'm going to look at it like that. No external torque. Okay. Now, if we want to understand the motion after the collision, we can also ask, is linear momentum conserved? Well, you can say all the momentum linear-wise is coming in from the ball, and then after they start rotating, is there any linear momentum there? And you might say, well, maybe we know there's angular momentum, but we can look at the end of a point and say there's linear momentum, and it gets all confusing. So there's an easy way to answer that. And again, it's looking at in terms of internal versus external. For linear momentum, we don't want to look at torque, we want to look at force. Okay, so is there an external force acting on it? Well, when this hits here, it exerts a force, but the ball is part of our system, so that's internal. So things look good. However, we can't forget about the pivot point. The pivot point does not exert a torque. I forgot to mention it earlier because there's no lever arm, but it is holding the stick in place from moving forward. So we can argue that there's some force due to the pivot point right there. So the answer is no, okay, because it introduces an external force, not a torque. So you got to look at force for linear, torque for angular. Okay, now we can ask then and answer what is the angular velocity of the stick afterwards. Okay, the ball and stick, I should say. So we know angular momentum is conserved. So let's start there. Sigma L equals sigma L prime. Okay, so what is our initial angular momentum? It's not zero. As I mentioned before, if I include this whole system, this has an mv and it's hitting it at some r, so that's going to be equal to mvr, but r is just half the length of the stick, so I'm going to call r L over 2. Afterwards, they're going to start spinning around and around and around, so the easiest way to calculate the angular momentum afterwards is I times omega. Okay, and that's the omega that we're interested in. So now it's just an issue of expanding this part here, the I especially. All right, so how do we calculate the moment of inertia of the ball slash stick? So let me draw the stick here. Here's the ball stuck to it. Okay, so there's actually two parts. There's a moment due to the ball, and then there's a moment of the stick itself, and we can separate them. So we can say I total, I'll just put a TOT here, is equal to the I of the ball, being a distance away from the pivot point, plus the I of the stick itself rotating about that pivot point. Okay, so treat the ball not as a sphere, it's not spinning, we don't care about that, but as some mass that's some distance r away from the pivot point. So in other words, we use a generic moment equation, which is the m of the ball, which is just m, times r squared. Well, r is L over 2, and so we square it, we get L squared all over 4. Okay, so make sure you can reason that out. For the stick, we've got to look that up. Okay, so if you go back to your notes and look up the moment of inertia of a rod that is pivoting about its center, you will see that it's 1/12 ml squared. Okay, so if I combine these two terms and make this common denominator of 12, I'll do the math for you. I get 1/3 ml squared. Okay, so there's the moment of the ball slash rod. So I'm going to go back over here, and I've got mv L over 2 equals 1/3 ml squared omega. I'm trying to solve for omega. So the m's cancel out. That's nice. That's why I made them both the same mass for that to work out. And I see omega. Bring the third over there, and I've got 3/2. I get L squared here and L there. So this L cancels out, leaving that. So that goes in the denominator, and I've got V over L. And voila, there is my answer. Notice that the V over L is like a V over R, which is like an omega. So the units work out. So that's how you solve that. So look that over, give yourself more time to understand that, and come follow up with questions. All right, there are two other problems here. I am quickly running out of time, so I'm going to make a second tutorial.